Welcome to the gas laws. So you should already be familiar with the gas laws. We've got Boyle's law, which says that pressure times volume is a constant at constant N. So N is number of moles or amount of substance. So at a constant amount of substance and constant temperature. We've got Charles's law, which says that volume divided by temperature is equal to a constant at constant number of moles and constant pressure. So Boyle's law says that pressure and volume are inversely related at constant number of moles and constant temperature. Charles's law says that volume and temperature are directly proportional to one another at constant number of moles and constant pressure. Avogadro's principle says that volume divided by number of moles is equal to a constant at constant pressure and temperature. And that means that volume is going to be directly proportional to number of moles at constant pressure and temperature. Then we've got Gay-Lussac's law, which is pressure divided by temperature is equal to a constant, again at constant number of moles and constant volume. And that means that pressure is going to be directly proportional to temperature at constant number of moles and volume. So these gas laws are limiting laws because they're strictly true only in a certain limit. That is, as the pressure approaches zero in this case. Although these laws are true only at pressures equal to zero, they are reasonably close at normal pressures with pressure around 1 atmosphere. That is, they're reasonable approximations for us to use most of the time as long as we don't have certain conditions. Those conditions are low temperature, where we might be close to the condensation point, the boiling point of our substance, or very high pressures. As long as we're around 1 atmosphere, then gases will approximate these equations fairly well. So we can plot curves for each of the gas laws relating the two variables, keeping the other two variables constant. So a set of isotherms, these are curves in which the temperature is constant, are plotted over here. So we've got pressure versus volume. And note that each curve here is a hyperbola. This is a curve with x times y equals a constant. And that means that we never actually reach either of our two axes. We can never get our volume to be zero, so the pressure just goes up and up and up and up and up. In order to get the volume to be zero, the pressure would have to be infinite, which we can't actually really have in a real system. And in order to have the pressure be zero, the volume would have to be infinite, which again, we can't have in any real system. And so instead of plotting pressure versus volume, if we plot pressure versus the inverse of volume, now we get a linear plot. And the slope of that line is going to depend upon the temperature and the number of moles we have. For a constant number of moles, if we increase the temperature, then that slope is going to increase. On the other hand, we could plot isobars, and these are curves with constant pressure. And they'll show the variation of volume with temperature. So we've got volume here, temperature down here. And at any one pressure, as we increase the temperature, we increase the volume. And that's going to be increasing linearly. And as we decrease the pressure, then that volume gets larger for that same temperature. On the other hand, we could plot the isocores, so these are curves with constant volume, showing the variation of pressure with respect to temperature. And so now, if we keep the volume constant, and we increase the temperature, the pressure increases. And if we decrease the volume, then the pressure increases. So note that in each of these cases, these plotted isotherms, isobars, and isocores also are keeping the amount of gas, so that can be N, constant. So we can combine each of these above laws to get the ideal gas law. And Atkins is going to call this the perfect gas law. So the ideal gas law is PV equals nRT, or Pivner. We can also rearrange that to give us our constant all on one side. So PV over NT is equal to R. Note that PV equals nRT is the more common form, but to put it in the same format that we've had earlier, it's this format. So now we can see all the relationships between our variables. We can see that if n and t are constant, then pressure times volume is equal to some constant. If we have pressure and temperature constant, then we have volume over number of moles is equal to some constant. And that's Avogadro's principle. If we have volume and number of moles constant, we've got pressure over temperature is a constant. And so you can see that we can, from the ideal gas law, we can go backwards and derive any of our previous laws. And R here is the gas constant, and it has values given in the table over here. This is table 1.2 from the book. And we have different units here. We've got the value for R with different units here. The top one is joules per mole Kelvin. The second one is listed here as cubic decimeters times atmospheres per mole K. That's going to be the same thing as liters times atmospheres per mole K. So if a gas obeys this equation of state under all conditions, then that gas is an ideal gas. A real gas, on the other hand, behaves more like a perfect gas the lower the pressure is and the higher the temperature is. So there are no real ideal gases. There are no ideal gases that we can actually point to. Not a single gas actually obeys the ideal gas law at all values for pressure, temperature, number of moles, and volume. Real gases deviate from the ideal gas law or the perfect gas law in some way, under at least some conditions. So if we now keep number of moles constant, if we keep n constant, we can then make a three-dimensional plot for our remaining three variables: pressure here, volume, and temperature. And so you can see that we've got now a surface here, not just a curve. We've got a surface here, but if we keep any one of the variables constant, so if we keep the temperature constant, and we're looking at, say, this plane, that's this bluish plane there, that's going to run along that temperature, you can see that as we decrease the volume, the pressure has to go up. And so that's our isotherm. We can look at an isobar, where we're keeping the pressure constant, and now we have a plane this direction, and we're looking at this curve there. That's our isobar, where now we're varying the temperature and the volume. And you can see that as the temperature decreases, the volume decreases. Alternately, we could look at the isochore, which is this one. And so now we are not changing the volume, we're keeping that value fixed, but we're altering the temperature and seeing how the pressure responds. So we see pressure is directly proportional to temperature, we see volume is directly proportional to temperature, and here we see pressure is inversely proportional to the volume. So now let's define two more terms. We've got standard ambient temperature and pressure, which is SATP. This is 298.15 Kelvin and 1 bar. This is the unofficial standard used by many chemists, including Atkins. Then we also have the standard temperature and pressure, or STP. This is 273.15 Kelvin and 1 atmosphere. This is the standard used by IUPAC. And note that before 1982, IUPAC defined STP as 298.15 Kelvin and 1 atmosphere. So this is 25 degrees C was used for STP before 1982. But in 1982, IUPAC changed the definition to be 0 degrees C and 1 atmosphere of pressure. So the standard temperature and pressure is 0 degrees C, 1 atmosphere, and standard ambient temperature and pressure is 25 degrees C and not 1 atmosphere, but 1 bar. Note that 1 bar is about 1% lower than 1 atmosphere. So the molar volume of a gas is the volume that 1 mole of that gas occupies. So the molar volume, Vm, is equal to the volume divided by the number of moles. So let's take a quick moment here to talk about the weather. So you've seen both isothermal and isobaric curves before. We've got isothermal curves in a map like this showing the temperature that we expect the air to reach during the day. So the high temperature. You could also plot the low temperatures as well. But this happens to be a map of the United States, and this is for February 10th, 2001. And you can see that we've got these lines on here showing the isotherms. So along any one line, that temperature is going to be constant. This is now across some region in space in the United States. So you can see we go from very cold temperatures up here. We've got -10 degrees, 0, and these temperatures are listed in Fahrenheit. 20, 30, 40, 50, 60 down here in the Gulf Coast. But you've also seen isobaric curves before. So when plotting storms as they move across the country, you can see there are some high regions and some lower regions. So where we've got the H indicates the higher pressures, and then those curves around there, so this curve here is indicating on that line there's a constant pressure, so that's an isobaric curve. And likewise around this line is a constant pressure, and then around this line is a constant pressure, and the pressure is going to decrease as we go. So you can see that the pressure is dropping as we go this direction, and likewise it's dropping as we go this direction from the high pressure to the low pressure, and this is then the pressure front moving through. So now let's turn to the kinetic model of gases, or the kinetic molecular model. The kinetic molecular model makes a few assumptions. Number one is that the gas consists of molecules of mass m in constant random motion. That is, those molecules are constantly moving around. It also assumes that the size of the molecules is negligible. That is, their diameters are much smaller than the average distance traveled between collisions. So the distance between molecules is much, much larger than the actual diameter of those molecules. And that means that most of the volume is simply empty space. Most of the volume is not occupied. Another assumption that is made is that the molecules interact only through brief, infrequent, and elastic collisions. So an elastic collision is one in which the total translational kinetic energy of the molecules is conserved. That is, no energy is lost to rotational, vibrational, or electronic transitions. So if it's a brief transition, it doesn't last very long. That means that most of the time our molecules are not colliding because those collisions are also relatively infrequent. So if the volume is halved at constant n and t, then twice as many molecules collide with the walls in a given amount of time. And that means that the pressure must double. So if we look at any wall, say that wall there, we've got some of our molecules moving towards the wall, and if they strike that wall, then they're exerting some force on the wall during that collision. And because we have a large number of molecules in there, that force is going to be roughly constant over time. But if we have the volume, so now there, we still have the same number of molecules, just as many of them should be moving this direction to strike that wall. But now the area there is lower. An alternate way of thinking about this is that if the area is the same size, we've got twice as many molecules per volume, and that means that we're going to have twice as many collisions. So either the area changes, like the left wall, or the area stays the same, like the top wall, but we have twice as many molecules striking that area. So the pressure has to go up. Now, increasing the temperature at constant amount of substance n and constant volume causes the average speed of our molecules to increase, and this means that we're going to increase the collision frequency. So our molecules are going to collide together more often, simply because they're moving faster. And that's going to increase the pressure. Those molecules are going to collide with each other. They're going to collide with the walls more frequently. More frequent collisions means more collisions in a given time. That means the pressure has to go up. But furthermore, each collision of a molecule with the wall now imparts more momentum to the wall because the molecules are moving faster on average. And that means that each collision imparts more energy. That means that each collision is going to impart more momentum to the wall. That means the force on the wall has to go up, and that means the pressure goes up. So the pressure is going up for two reasons. One, we have more collisions in a given amount of time, and two, each collision that we do have, which we now have more of, each collision is hitting harder. So the pressure is going up for two reasons, because the collision frequency is changing and that collision, the momentum transfer of each collision is going up. So it can be shown, and it's going to be shown in chapter 20, that the pressure and volume are related by this equation here. So we've got pressure times volume is equal to 1/3 N times capital M times C squared, where M is lowercase m times N sub A. This is Avogadro's constant, as Atkins calls it, or Avogadro's number. So M there, remember, lowercase m is the mass of one molecule. Well, if we multiply the mass of one molecule times Avogadro's number, that's going to give us the molar mass. So capital M there is the molar mass of our substance. And C there is the root mean squared velocity of the molecules. So again, M is the molar mass of the molecules, N sub A is Avogadro's constant, and C is the root mean squared speed of the molecules. And V is then the speed of the molecules, the velocity of our molecules. So if the root mean square speed of the molecules depends only upon the temperature, then at constant temperature, pressure times volume is equal to a constant. And furthermore, that right side of the equation then must be equal to nRT. And that means that the root mean square speed of the molecules, so we can basically rearrange that last formula to give us this. So the root mean square speed of our molecule C is equal to the square root of 3RT over M. So 3 times R times the temperature divided by the molar mass of our molecules. And that means that the root mean square of the speed of our molecules of a gas is proportional to the square root of the temperature, so square root of T there, and inversely proportional to the square root of the molar mass. And therefore, molecules of a higher temperature gas are going to move faster, and molecules of a lower molar mass gas will move faster at the same temperature. So, at 298 Kelvin, nitrogen molecules have a root mean square speed of 515 meters per second. And this means that at normal temperatures and pressures, the molecules of air collide many, many times every second. So for homework, you should calculate how often nitrogen molecules in air at SATP are going to collide. So note here that we've shown how fast they're moving. You should be able to figure out how often those molecules are going to collide. That is, what is the average time between collisions for nitrogen molecules at SATP? In a mixture of two or more gases, the partial pressure, P sub J, of gas J is defined like this. So we've got the partial pressure of gas J is equal to chi J times P. So chi there is the mole fraction of gas J. So P is the total pressure of the mixture, that's this P here. Xj, or chi J, is the mole fraction of gas J. So the mole fraction is the moles of J divided by the total number of moles in the mixture. The total number of moles is the moles due to component 1 plus the moles due to component 2 plus the moles due to component 3 and so on, including component J, going up until we run out of components of our mixture. So it then follows that the total mole fraction is equal to, so X total is equal to X1 plus X2 plus X3 and so on, and that has to be equal to 1. It also follows that the total pressure is equal to the sum of the partial pressures. So P total is equal to P1 plus P2 plus P3 and so on, which is also equal to the quantity X1 plus X2 plus X3 and so on times P, the total pressure. And that was the gas loss.